Hi everyone, welcome to today's presentation on AI implementation based on compiling neural networks from Scade language. My name is Max Nayourk. I'm working as a senior embedded system expert here at ANSYS, and today's presentation was supported by Bernard Dion and Jean-Louis Colosso as well. So on the agenda for today, we're going to start with the proposed AI workflow. We're going to talk about different considerations on neural network representation. I'm going to give a deep overview on the Scade language and the code generation capabilities as well, which we will leverage in order to look more into depth how we can use Scade for the implementation of neural networks. We are then going to discuss more globally again about the certification aspects of neural network, and then I will provide a summary and conclusion. So let's get started. Many of our customers are facing some very great new challenges like urban air mobility. We will see that city skies will be more crowded than ever before, and this brings new challenges to the guidance, navigation, and control of vehicles that need to maneuver these environments safely and efficiently. Now, this typical guidance, navigation, control task consists of a vehicle that has to fly through a certain set of waypoints while avoiding safe distances to obstacles, ground obstacles, or other air traffic. And here's an example how this can look like. So in this example, we have a neural network that is controlling the aircraft, and we can see that the aircraft is trying to maintain this orange waypoint. Now, this being said, we manually perturbate the vehicle using the joystick. So I'm pushing away the vehicle from the target waypoint. With the moment I release the joystick, the AI controller takes over again and navigates the aircraft back to that waypoint and maintains it in a stable position around the waypoint. Now, this demo and this example is going to guide us through the presentation today. So let's take a look more carefully at how the learning process works. So for this demonstration, we have been using a technique called deep reinforcement learning. In deep reinforcement learning, we have an agent that is controlled by the neural network. So in our case, the neural network and a bit of conventional software around it. And that agent interacts with an environment that performs the dynamic simulations, an example. And also part of the environment, there's a critic that's going to give a feedback to the agent itself on how well it did. Also from the environment, it's going to compute the next state of the simulation that is passed as observations through the agent. So you can think about it a bit like when you were learning to drive. You were sitting in a real car, driving around in the real world, with your eyes observing the environment, with your hands having the controls over the vehicle. Now, while driving around, you had an instructor next to you telling you how well you did. And when you did something good, you would get an incentive. When you did something bad, you get a bad remark on your driving skills. So based on this trial and error approach over iterations, you learned how to safely drive a car. And now we can do the same with aircraft, but of course we don't want to have them fly around randomly in the sky, crashing every now and then. So we need to bring it to a simulation. So for our problem statement, we have formulated our agent to observe its own position of the aircraft, the rotation, so roll, pitch, yaw in the space, as well as the direction and distance to the next waypoint. In terms of action, the neural network controls the desired thrust and the desired roll, pitch, and yaw angles, while a subsequent traditional controller is making sure to control the aircraft itself on these desired angles. In terms of rewards, we give positive incentives whenever a waypoint is reached, and a highly negative reward when an obstacle is hit. And also, in order to get the agent going in the right direction, we give it a slightly positive reward whenever the distance to the waypoint is reduced. Now, the beauty of reinforcement learning is that we can come up with any sort of reward function. So whatever objective we may have in addition, like going efficiently, going quickly, whatever you want to think of, this can be added to the reward function, and the agent will learn the corresponding optimal behavior. Now, bringing these pieces together and, as said, moving it to a synthetic simulated environment for safety reasons, we have started with our training toolchain. In the training toolchain, we need a learning framework, which we took as an open third-party tool. In addition to the learning framework, we need to give it access to the actual vehicle simulator, the environment that's going to compute the dynamics of the vehicle, that's going to compute the next simulation state. And adding to this simulator, we have our Scade embedded code. So that's the part with the conventional software. So that part that takes the neural network action and put it into a conventional control command for control surfaces. And basically, in addition to that, also a Scade-based reward function. So everything which has the incentives and penalties is contained by the Scade reward function. So this in itself brings together the three elements which we need for a learning problem. And in addition to that, we have added a data analytics module, which we'll see in a second, that helps us to understand what has been learned. Now, I want to give you some insights into the very early iterations that we ran on this proof of concept. And here are some snapshots from the actual training phase. So in the beginning of the training phase, basically the agent is completely new to flying aircraft. It's just trying out random actions. And that's what we can perfectly see. It's fully random, it's crashing a lot. But after a first set of maybe a few hundreds of iterations, seeing the bad reward it gets for trying out things randomly, it somehow learns to prioritize actions which will not crash the aircraft. So trying to maintain a safe separating distance from the ground. And this is what we can see now. During the mid stages of the training process, we are somehow keeping away from the ground, but the agent has obviously not learned yet a notion of this target waypoint to be held. So more towards the end of the training process, we can now see that the agent has more notion of maintaining the target waypoint. It's maintaining a position somehow close to the waypoint, but still we have like this extremely shaky motions with all the bang bang effect, and certainly some behavior which we would not feel comfortable putting into a real aerospace system. So based on their first learning result, we wanted to understand what has been learned and what has not been learned. And this is where we leverage the data analytics. Now, one example of data analytics we performed is a sensitivity analysis that studies the mapping of the inputs to the neural network and the computed responses, outputs of the neural network. So here we can see the inputs to the neural network as discussed, like the distance to the target, the three components, the three dimensions of the distance to the target, then the pitch, roll, and yaw angles, as well as the vehicle altitude. On the left-hand side, we see our actions, our outputs, the acceleration command, pitch, roll, and yaw command. Now, from this analysis, we can learn some very good insights. For example, if we focus on how the vertical distance to the target affects the acceleration command, we can reason that as engineers, that when the target is above, we need to accelerate to reach the target. When the target is below, we need to decelerate the aircraft. And that's why this mapping between the vertical distance to the target on the acceleration command is something which we certainly expect as engineers, and that makes sense to our knowledge. Now, on the pitch command itself, we can see it has a strong dependency on the longitudinal distance to the target, which makes sense, and on the pitch angle. So that looks quite solid. And now if we look at the roll command, things start to get a bit odd. Firstly, the roll command is also depending on the longitudinal distance to the target and also the pitch angle, which really doesn't make sense from our point of view. Now, if we look at the yaw command, we see there's totally no dependency of the yaw command computation on any of the inputs. So certainly we can reason that the yaw command has not been learned at all. So based with this input, with this understanding, we went back to the training process. We improved the implementation of our agent, the simulation, and our learning problem itself. And here is how the results look like. So we can now see this perfectly stable behavior of the aircraft which is exactly the results we wanted to have. Now, the big question is, if we rerun our simulation and the analysis, the sensitivity analysis, can it validate what we observe here practically? Now, looking again back at the analysis itself, we can see that the dependency of the acceleration command on the vertical distance has improved. We can also see now this very clear mapping of the pitch command on the longitudinal distance and the roll command based on the vertical distance. So there's little interdependencies between the two commands, which is again exactly what we expect. Also on the yaw command, we can see some significant improvements. So all in all, we can say yes, the new sensitivity analysis confirms the impression which we had from the pure simulation. Now, this is good for understanding what has been learned, improving the training process to get a first understanding if it is successful or not, but it's not yet any sort of proof of safety. And that's what we leverage the validation toolchain for. In the validation toolchain, we take the AI model, or the neural network model contained in the neural network framework, and import it into Scade. So we will have one model containing both the conventional software as well as our neural network functionality. Now, this combined embedded functionality again interacts with our vehicle simulator to perform a closed loop simulation. And again, we use further data analytics to understand what's happening. So the data analytics module, in a kind of a Monte Carlo fashion, is running the iterations, is driving the scenarios, and we assess whether certain KPIs, safety KPIs, are met. Now, here is in the example of the closed loop simulation. So we can see the scenario and the graphical representation of the scenario, and that provides the sensor inputs to our embedded software. The embedded software contains both the neural network as well as the conventional control laws, and it's computing finally the commands of the aircraft. And then again, the simulator takes over, computes the next state, and the whole loop continues. Now, using this closed loop simulation with the data analytics allows us to perform reliability analysis. Now, in the reliability analysis, we vary the scenarios in a statistical fashion, and we then compute the failure probability. So in our example, the safety limit was defined as 20 meters. And we can see from the results that none of the scenarios that has been computed actually violated this safety limit. Now, clearly, when we compute the failure probability, we achieve a probability of failure of 0, as we had only safe designs or safe scenarios. And so that's kind of the proof, the statistical proof, that our function that has been trained, that consists both on the neural network as well as the conventional software, is actually fit for the purpose of flying this aircraft in that specific domain we have been looking at, in that specific kind of scenarios. Now, having established this global argument that the function has been learned correctly and is safe to operate, is one of the very important key aspects of the whole safety case. But we still need to demonstrate that what has been learned, what has been contained in this model, is safely implemented into the target embedded software. And again, I want to stretch on the fact that we as Scade, we can combine both the conventional function with the conventional controls we need, plus the neural network imported from one of the well-known training frameworks. So we import it to Scade, and then on the integrated and combined and validated model, we then use qualified code generation to generate the code for the embedded target in a qualified fashion. Now, the next section is now talking a bit more about the representation of neural networks. So the most natural representation of a neural network, and let's talk about the example of TensorFlow, is the TensorFlow compute graph contained in the protobuf files. But typically those contain the full learning problem, meaning the forward pass through the neural network, the backward pass, all the loss functions and other iterative algorithms that you need in order for the training to happen. This leads to the fact that only a very small aspect of the actual model representation is the forward pass of our neural network that we need in order to compute the inference. Now, this being said, when we import a neural network into Scade, we only focus on what's needed for inference. And that's what we can see here, this very concise notation of the same neural network formally represented in Scade language. Now, of course, when we use models during our development process, the consistency between models, between the phases of training, validation, and implementation is absolutely key to achieve a safe implementation. Interestingly, I've been following some tech talks recently, and one of the key insights was that every neural network framework sometimes considers a slightly different mathematical implementation of the same neural network. An example, for convolutional neural networks, the padding may be a bit different from one framework to the another. Certainly, these inconsistencies could possibly introduce some great harm to our development process. And that's really why we want to establish a process that maximizes the consistency, and especially between the validation and the implementation phase, ensures the consistency of the models. Now, if we look at the idea of implementing both the traditional and AI-based software in Scade, we have one coherent Scade model that represents all in one. And this actually supports the idea of consistency through all the phases, which we're going to explore more in the next slide. Now here we can see again the different phases of implementation and even adding a training preparation phase. So what's very important to emphasize that with the proposed flow, we very early start to implement the traditional software and directly do it in Scade. We have seen the control laws being implemented in Scade and even the reward function implemented in Scade to have one base for everything we do, one software base to make everything consistent. So after the initial phase of the preparation phase where we do all the surrounding functionality that we need, we directly use the Scade models of the conventional software for our training process. Now, the training process clearly produces the machine learning model that, as we have discussed, is directly imported then into Scade again. So, which means from that point in time, we have one concise, one unique design model that captures the whole functionality. And based on that model, we perform all the validation activities like the reliability analysis, the sensitivity analysis that we have seen, and also perform the final qualified code generation for our target software. Now, having talked about the consistency and the global flow, we now want to dive a bit deeper into the Scade language itself and the code generation properties to see, to understand the basic principles that we can then later leverage to implement the neural network. Now, Scade stands for Safety Critical Application Development Environment. And it's not just a tool, but it's also a known domain-specific language that is formally defined as a language and can be used by anyone. Now, Scade language is dedicated to real-time embedded software. It's based on the synchronous language principles. That means every parallel composition is finally deterministic. It's defined and documented independently of the toolset, and it really focuses on safety. So therefore, it has some strong statically guaranteed properties, such as being strongly typed, allowing only safe array operations. It's bounded in time and memory, so there's no dynamic memory allocation. It always has defined output values, so it cannot depend on any initialized memory. And when using parallelism, it's scheduled as static sequences, which enables the generation of sequential and deterministic code. Talking about code, from the language we can leverage the Kcg Code Generator that is qualified to DO330 TQL1 which we'll discuss a bit more into depth in a minute. When we model using Scade, we have two possibilities of modeling with Scade. One is leveraging Scade models in a graphical representation. So we have nice data flows as an example here. Or we can use textual notation, especially when we want to auto-generate something like a neural network model. The textual notation will come in extremely handy, while for the traditional software, we typically use the graphical notation because it's just much more comprehensible to a human being. Also, Scade brings us the benefit of allowing us to combine state machines and block diagrams into a single language. So we can have the main states of our system, of our software, represented by state machines, while the precise numerical computations, like traditional PID controls or a neural network, can be modeled in block diagrams and computed at every cycle, the precise numerical value. Now, talking a bit more about the Kcg Code Generator. The Kcg Code Generator translates any sort of model defined in Scade language into C or Ada code. And it's fully qualified. And within that qualification process, we aim at ensuring that the generated code implements the function defined by the model. That means that the generated code from our side is verified with regards to the semantics defined in this language specification. And furthermore, we show that the code generation options only apply to the shape of the generated code, but do not affect the function specified in the model. So independent of the code generating settings, the function implemented is still the same. Last but not least, in having these kind of qualification activities and proof allows us to take certification credit in the sense that customers applying the Scade Kcg Code Generator do not have to undergo manual activities of verifying that the code generated complies with the model. That's what the qualification does. It states and it guarantees that the source code generated implements the model that has been specified. The last subject I want to talk about is the model coverage applied on the Scade model. So Scade models allow us to measure the coverage on the model level, and this is defined by looking at different coverage points. So here you have an example, the blue dot S, which is one of the coverage points, and by definition a point is considered as covered by a test when it shows its ability to contribute to one of the outputs. So that's basically generalizing the idea of the masking MCDC coverage. As a consequence of that, it means that if we have 100% coverage on the model level, and because we have been using the Scade language and the qualified code generation procedure, it implies 100% coverage on the code level as well. Because the model coverage tool is qualified at TQL4, it allows customers to give or to get credit for both the code coverage as well as the model coverage activities which you have to perform. So you can do both activities in one go on the model level. Now, this is very good for all kinds of conventional functionalities like the PIDs, which we need to control the vehicle. For the neural network, we see this certainly as a strong requirement. So we expect that even for neural networks, we have to perform coverage analysis. But for neural networks, the coverage itself is not sufficient to prove the absence of unintended functionality. And we will see in the certification section what complementing means we may leverage to really show the absence of unintended functionality. Now, having taken a deeper look at Scade as a tool and as a language, we now want to see how we can use Scade in order to implement neural networks. Now, the most important features for neural network computations are certainly arrays and vector operations. So if we talk about vectors in Scade, we mean arrays, and arrays by definition in the Scade language are one-dimensional features. However, we can nest these, we can nest arrays into each other to create multi-dimensional features. Also, what needs to be said is that arrays in Scade are by definition safe, in a sense that the size of an array is part of the type and the type checking, that the access to an array is always done within bounds, and that arrays are always completely defined. Finally, array manipulations are always done through safe operators, through iterators like the map and fold operators, which we'll see in a second. Additionally, on arrays, we can use the concept of polymorphism that allows us to create array operations with generic types and array sizes. So concluding, the expressiveness of the Scade language is enough to specify the neural network layers, and therefore Scade allows us to write generic libraries of neural network layers, then compose the libraries into neural networks, and then take all the certification credit that we have discussed when you go for your software certification activities. Now here's an example on how a neural network library in Scade looks like. So let's start with the inner product. Here we can see the generic definition of the inner product computation. It gets two parameters in terms of dimensions, in terms of size, which is the size of the input vector and the size of the output vector. And then we can see the three inputs to that function, which is the input vector from basically the result from the previous layer, the weight of the individual layer, and the biases. And based on this, and based on the array operations, we can then compute the output of the layer. Now, if we want to bring it to a multi-dimensional level, let's say 3D operations on a 3D space, we simply add the additional dimensions and the additional inputs and use map and fold operations to iterate through the nested arrays in order to perform the same kind of computations. Additionally, you can see that it's fairly easy to define layers such as ReLU layer or softmax activation layers. So this is something which can be done simply and which we provide in the neural network library. Now, having these basic layers allows us now to implement more complex neural networks like LeNet5. So in the beginning, we see now the definition of the different layers, now the types and the sizes of the different layers. And then we use the different libraries on the different layers in order to implement each layer. An example, we've talked about the 1D inner product. We can now see it being assigned the concrete size values and also the in-layer, the weights, and the biases that are, for instance, imported from the neural network example in TensorFlow. Now, while this is the textual representation, we can also do the same thing in the graphical representation. So if you want to model complex neural network architectures in a graphical fashion, that's perfectly doable. So having talked about how we can implement a neural network in Scade language, having talked about the qualification and the qualification credit we can take from the language and the qualified code generator, let's continue now and to discuss how this fits into a certifiable flow. So firstly, let's look at today's certification basis, certification standards, in our case DO178C and the model-based supplement DO331. So in DO331, we have several options of how we can use models. An example, we can use a model simply in order to represent our software design. We can use model to represent both the software requirements and the software design, but we can also use models starting actually from the system level. And that's kind of similar to our case. Now, if we think about this as regular controls like PID controls, we would typically have a model for this already on the system level, and we can directly obtain code from it. And this is similar how it behaves with the neural network. If we think about it as a controller, it's positioned on the system level, capturing the precise controller, and we can directly generate the software from it. So that's actually quite in line with the DO331 examples. Now, if we think about the software development workflow, based on conventional Scade projects, I would say. We have the typical activities of requirements, models, source code, and object code. And typically we implement manually the Scade model. We check it conforms to standards. We trace it back to the system requirements, or the requirements from which the model is derived. And we also perform functional verifications through model simulation and model coverage against these requirements. We then generate the source code by the qualified means. As we have emphasized on today, there's no need to verify the source code against the model because of the tool qualification. And then we have the we can compile and build the object code and finally, again, verify everything against the requirements. Now, if we put this into the idea of an AI-based development process and using machine learning models, we actually find out that there are a few things which are tricky to impossible to do with neural networks. Firstly, the machine learning models, like the individual parts of a neural network, like the weights and activations, are hardly traceable to requirements. We cannot tell which precise part of the neural networks implements a certain requirement. We have it as a whole, it does something, but we cannot trace it easily to the individual part of the neural network and the individual requirement. And this brings us a problem for the functional verification. So without traceability and without this detailed understanding, we're not able to derive equivalence classes, which basically makes the traditional requirement-based testing impossible. Now, this is where we need to introduce new means in order to achieve these objectives. So let's look a bit onto the next slide to understand better how model simulation is typically used and how we may be able to use it in the future to achieve the same objective by new means. So typically on host-based testing, we use the same model to generate the code used for host-based testing as well as for the final target. Now, as we said, the host-based testing is not sufficient. So here would come our additional means of verification, validation, verification, such as the sensitivity analysis that we have seen early in the presentation, as well as the reliability analysis. Now, what's extremely important about this step, we have talked about the qualification of the code generation, meaning as long as we use the same Scade model, the different sorts of code used for the different steps is guaranteed to behave similarly, identical. Now, let's look more into the credit we can take from model simulation. So the model simulation is largely expected, so the host-based model simulation is largely accepted to demonstrate the compliance of a model with its requirements. Now, this being said, it's typically required that certain aspects are again reassessed on the target, in example, numerical accuracy. Now, the point is that when we have numerical computations, they may work slightly differently on one target platform than the other. And actually, the neural network may be extremely sensitive towards these fine differences. So certainly proving the numerical robustness is a very key requirement in order to guarantee the safe implementation of a neural network. And this is one of the open challenges right now. We are working very actively to find means to perform this proof of robustness. And it's one of the topics which is also a lot discussed in different standardization committees. So it's one of the open topics. Now we're getting to the end of this presentation. So let's summarize what we discussed and draw a conclusion. Now we have seen that AI-based functions allow us to increase the level of autonomy. We have seen how we can use reinforcement learning techniques, have very sophisticated reward functions to put all kinds of objectives and learn a single control law based on them. We've also seen that AI certification remains challenging, but with a large contribution onto the different standardization committees in that domain, there's a lot of progress. So we are very confident to see AI in safety critical applications in the near and mid future. Also in this presentation, we have proposed an end-to-end flow for the verification and safe implementation of AI in embedded software, where we have started with a trained neural network model coming from TensorFlow or similar format, where we have obtained a formal software model through the import into Scade and combining it with the traditional software, where we have then proceeded with results analytics, in our case, the sensitivity analysis, to get a better understanding on how the neural network has learned its function, and then basically continuing in the closed loop validation of the function using reliability analysis. And then once we have shown that we can understand and it's reasonable what has been learned, and from the closed loop simulation that is safe to operate, given the failure rate we have computed, we can then utilize the qualified code generation in order to generate safe source code for our model. So thank you very much for attending this presentation. I hope it was interesting for you, and stay safe. Thank you.